All right, ladies. Let's talk a little bit more about torque. Okay? So if you recall, last time we were talking about the formula for torque, and we defined it as a force times the distance, but these two have to be what? Perpendicular. So I want to just mention something. So let's imagine that this angle is 30 degrees, okay? And this force is, let's say it's 10 newtons. And let's say the force is being applied at this point, and the radius r, let's say it's 2 meters. What would the torque be? So what would it be? So what component would you need? Do we need you would need this component, right? So you need this component, and that would be the opposite side, so it would be the radius, so r, 2 times f, which is 10, in this case times sine 30, and that would give you, 2 times 5, which is 10 newtons meter, correct? Okay. I just want to point out one thing. You don't need to get the perpendicular component of the force, because what you could do is you can get the perpendicular component of the length or the radius. So in other words, this is equivalent, right? Instead of getting the perpendicular component of the force, I can do this. I could say, well, what's this component, right? So in other words, my force is 10, but what's my perpendicular component for my distance? So that would be r sine 30 in this case, because look, here's r. This is a triangle, right? R is my hypotenuse. What would this be? If I called it L, what would it be? It's the opposite side, and that's my hypotenuse, so it would be what? It would be r sine 30. And if I did that, I would get the exact same answer, which is 10. Okay? So it's just a thought that when you're doing these questions, you can get either the perpendicular component of the force or the distance to the pivot point. Okay? One or the other is, as long as the force and the distance are perpendicular, it's fine. Okay? Just wanted to point that out. Okay, so let's look at, yesterday we were looking at some examples with using torque and using it to solve static scenarios where things aren't moving. So let's look at 2 more questions. That's it. Okay, so we'll finish pretty quickly today. All right, so let's look at this question where we're going to figure out F1 in the following scenario.
Wow. Oh my god.
Okay, so let's figure out. Let me put in some numbers here, okay? Let's put in some numbers. Let's say that the beam, so we have a person who's on a bench, okay? The bench is like a beam. Imagine that the distance, so let's imagine that the length of the beam from this point to this point, let's say the length of the beam is, let's say, 5 meters, okay? And we'll call this F1, and we'll call this F2, and F1 and F2 are basically due to these supports, and they're the same distance. So we'll say that this distance is half a meter. So that's 0.5 meters. So that would be the same on this side, okay? 0.5 meters, okay? Let's say the beam, the mass of the beam is, let's just say it's 10 kilograms, and the mass of this hefty young lady mass of this lady is, we'll just say 60 kilograms. Okay. Now, we want to know what are the forces at, well, we're going to calculate F1 and actually and F2. Okay, we're going to calculate F1 and F2. Now, do you think they're going to be the same? Because you'd be like, well, why can't we just take the mass of the girl and the mass of the beam, and we have our downwards force, right? And then the other two forces have to be equivalent up, and why can't we just make them, the same? Yep. Exactly. Because there's actually a torque involved here, right? Now, the net torque will be 0, as you will talk about, but because she's not standing in the middle, then we can't assume F1 and F2 are the same. Actually, where is she? I gotta point that out. So let's say she is 1 meter away from F1. So let's put her at a distance 1 meter from F1. Okay? So this is what we're going to do. First thing we're going to do is we're going to start with the concept that the net force is 0, okay? So we know that the net force is 0, which means, well, what's acting down? Down? Right, so it would be the girl's mass. So it's going to be mass of the girl, mass of the lady, plus the weight of the lady, plus the weight of the beam. Now, well, you know what, we'll make that negative. We'll just stick with that being negative, plus F1 and F2 going up, right? So the weight, we would imagine that the weight of the beam and the girl, plus the F1 and F2 should equal to 0, right? Because there's no net force. The other thing that's true is there is no net torque. So there's no rotation in this system, okay? Now, when we do a torque scenario, you have to pick a pivot point, okay? So let's say we pick this as my pivot point. Okay, so here it is. So that's the pivot point. The good thing about doing that is you eliminate F2 in this scenario with the net torque, because if F2 is at the pivot point, what's this torque? It's 0 because R is 0, right? So then if we're looking at torque, the girl's going to generate a force acting down, right? And that's going to cause this system to rotate. So if that's the pivot point, which way would it rotate? She's pushing down, so imagine that she could move this beam. Which way would it rotate? It would rotate this way, right? That would be clockwise. What about the actual mass of the beam? So for any time you have a scenario like this where you assume that the mass is evenly distributed, the mass of the beam, we're going to look for the center of the mass. Sorry, the center of the beam. Where would that be? The beam is 5 meters long. So it would be 2.5 meters from the edge. So in other words, if this is 0.5, it would be about here. And that distance, I shouldn't be drawing an arrow pointing up though. Hold on. Let me fix that. Okay. That distance is at this point, which is 2 meters from here. Okay, 2 meters from here and 2 meters from here. Does that make sense? Okay, so there's our center of mass. So 2.5 meters from the edge, but 2 meters to our pivot point. So when we look at the net torque, you have the girl who's going to want it the beam to rotate clockwise, but also the beam is going to want to rotate clockwise just because of the mass of the beam. Yep. Clockwise. Yeah, clockwise. Because look, she's going to push down, which if this is a pivot point, would rotate this way. The beam is going to be pulled down by gravity in the same direction of the girl, so the beam is also going to want to rotate that way. What's going to cause it to rotate the other way and balance it out is F1. F1 is going to push this way, which will cause it to rotate the other way. But since there is no rotation, that means they all what? They all cancel out. Okay? So let's write these out. So let's say we'll make counterclockwise positive. So we can say that F1 times, what's R? How far away is F1 from F2? 4, right? So we can say F1 times 4 minus the torque going the other way. So that would be the girl's torque. So it would be her weight. So that would be the weight of the girl times how far away is the girl from the pivot point. So it would be 3, right? Because she is here 1 meter away from F1, which means 1 meter away from the center, plus another 2 meters away from the pivot point. So she's a distance of 3 meters from the pivot point. And what about the mass of the beam? How far away is the mass of the beam from the center of the mass to the pivot point? It's 2. Yeah, it is 2. So, sorry, it's supposed to be F. So the weight of the beam times 2. Okay, so let's figure this out. We could say that F1 times 4 has to equal the weight of the girl. Now, what's the weight of the girl? Well, the weight of the girl will be what? Her mass times 9.8. What is that? 588 times 3. Okay, now remember, this is negative, right? So this is actually negative 588 times 3 minus. So if I move this over, it becomes negative, but then the negatives are all going to cancel out. So I'm just going to get rid of the negatives, all right? The negatives are all going to cancel out. So what's the weight of the beam times 2? 196. Okay. All right. So we have F1 times 4. So we get rid of the 4. So what's F1? So 588 times 3 plus 196. What is it? 490? 490. Now we have F1. We can go back to here and figure out what F2 is. So if we rearrange this, we could say that F2 would be basically the weight of the girl plus the weight of the beam minus F1. Okay, so let's figure out what F2 is. So the weight of the girl was, what was it, 588? The weight of the beam was 98. And F1 was 490. So what do you get? 196 we got? Okay. And then as always, you should just see if that answer makes sense. Does it make sense? Where's the higher force in this case? Yeah, and does it make sense? Well, she's closer to F1, so yeah, that does make sense. Okay? So there's another example where you can use torque to figure out the forces. In this case, it would be like on a beam or a bench. Okay? We'll do one more example. Now this one is going to be a little bit trickier, but it's really just the same thing. Okay? So we'll do something that's hanging like a sign that's hanging. But sign hanging is kind of boring, so I have this for you. All right. Okay. So should have been doing this from February. I don't know why it wasn't doing this before. Okay, so let's take a look at a question like this. I have to give you some numbers. I haven't put any numbers in. So let's imagine that we have a person who's hanging. This could be like I don't know, some sort of a swing set or something like that. Let's make this angle 40 degrees. Let's make this angle 30 degrees. Okay. And we're to make things easy, we're gonna say that the beam is 0. Okay, has no mass, just to make life a little bit easier for us. Okay. So we have tension in a cable, and then we're gonna figure out the force of the floor and the wall. It's gonna give you one more piece of information. Well, actually, I'm gonna give you two more pieces of information. I got to give you the length of the beam. We'll just stick with 4 meters, and the mass of the individual. We'll put him at I don't know how much he weighs, what his mass is. So let's say we put him at 90 kilograms. Okay, we get a big lunch. All right. Now we're going to figure out the force of the floor and the force of the wall, okay? So one quick question. The floor would be here at this point. Which way do you think the floor would push? Up, right? So the floor would push up. So there's my force of, don't be confused with, it looks like force of friction, but in this case it's the force of the floor, okay? Which way would the wall push? Yeah, to the right. Whoop, what happened there? It would have to push to the right, because you can kind of imagine that there's going to be a force acting this way, to the left, right? Because you can see the cable is going to be pulling up and left. So we can imagine that the wall will be pointing to the right. Okay? So again, we did the exact same thing we did before. We know that the net force is 0. So that would be what? What are the forces acting up and down? So what's acting up? Yep. So up would be the floor. What else? What component of the cable though? Right. So it would be this component. So what would that be then? That would be Ft times what? Yep. Very good. And then what's the only thing then acting down? Because remember, we're going to make it easy and there's no, the beam has no mass, okay? Yep. So that would be the weight of the person, which we labeled P, because you all know who he is. Those watching on YouTube will have no idea who he is. That way I won't get any grief. Okay. So that's, by the way, that is the net force in the Y. Let's also consider the net force in the X direction. We know it's going to add up to 0. What's acting along the X direction? Yep, force of the wall. To the right, and what's acting to the left? Yep. But what component of tension? Very good. So it'll be the horizontal component. Okay. Now, we still have, in this case, we have three unknowns, right? We don't have the force of the floor, we don't have the force of the wall, and we don't have the force of tension. It's bad enough to have two unknowns, but now we actually have three. But we have one more thing we can look at, torque. Okay. So let's look at the torque. Let's change the color there. So let's take a look at the torque. We know it's not rotating. Well, we're assuming it's a static scenario. It's not rotating. So that means the sum of the torque is 0. If we pick this as our pivot point, then we actually eliminate two forces. Right? What do we eliminate? Because what forces are at the pivot point? Nika? The floor and the wall. So we eliminate two of them. So what are the only two things causing rotation then? Well, we have the mass of this individual, so it's weight, and that force is being applied at a distance of 4 meters. We can get that perpendicular component. Okay, we can get that perpendicular component. So what would this angle be? What should that angle be? What do you think it should be? Yes, it should be 50. It should be 50 degrees. Is that one of the things you guys learned in math about like the Z pattern or something like that? Okay. So that should be 50 degrees. So we can figure out what this component is. So we can say the force times R times sine 50. But we talked about before, what's something else you could do? You don't need the perpendicular component of the force. You could get the perpendicular component of the length. Okay? So either way would work. Alright. That will cause this to rotate this way. What will cause the beam to rotate the other way? Yeah. Okay, so what's that force? So tension. Well, what's that angle? Well, if this is 50, that has to be what? There's your Z pattern, right? There's your, I remember that from high school. And I had hair back then. I remember that. There's your Z pattern. So if that's 40, which would make that 50. Okay? So that means that this angle is what then? 70. So Ft times R times sine 70 is your other torque. Okay? So now guess what we can do? We can solve for Ft, right? Because we have the mass of the individual, we could say Ft times R sine 70 equals the weight times R times sine 30. We could get rid of this. You notice the R is going to cancel out. Okay, so what's Ft? So it's the weight of the individual. So it's 90 times 9.8 times sine 30 over sine 70. What does that give you? 460. Okay, we'll just round off to 469. Okay, now we can go back and figure out the force of the floor, because we have now, if you look, we have the tension and we have the weight. So we can go back and solve for force of the floor. So the force of the floor then, if we look at this equation up here, would be the equivalent of, if I move this to the other side, would be this, if I move these two components to the other side, it would be this minus this. Because this will become positive on the other side, and that will become negative, right? So the force of the floor then would be the weight minus the tension times sine 30. So the weight would be 90 times 9.8 minus the tension times sine 30. Okay, what do we get for the force of the floor? Yeah, Laura? Where? For this one? In the green? So this is sine 50 because we're looking at the torque from this individual. The angle is 50 degrees. Where? This one? Did I make it? Oh, is that supposed to be 50? Ah, you're right. You guys caught that now? You're supposed to be watching me. Very good, Laura. So that's supposed to be sine 50. Okay, can we change this then? That's okay. Okay, sine 50. Very good, Laura. You're on your game today. Okay. Is it the same answer? Okay, what's the answer? That's okay. What is it? 719? 719? Okay. So that would be, so all we can do now is just change this to 719. Okay. Anything else? I think that's it, right? Okay, so what's that force of the floor then? $522.5, so we'll just say 523. Okay. And then the last one is the force of the wall. So you can see here, the force of the wall is equivalent to the tension times cosine 30, right? You can see it right here. So the force of the wall is equal to the tension times cosine 30. So that would be, tension is what? 719. So 719 times cosine 30. What would that be? So what's the force? Sorry, what is it? 622.7. Let's round it off to 623. Okay? Yeah, you're right. My 50 looks like a 30 there, doesn't it? Okay. So, that's it. Those are two more examples using torque. All right, ladies? And that is it.